All right, so this video is going to go over the general linear time invariant solution. So we went through solutions for mv dot plus cv is equal to f. We could figure out if we transform this into a state space model by replacing v's with our x's and our f with u. We can figure out what the state space model looks like and solve for that. However, we needed to know what u of t was when we were doing our trial solution method, and we really only did it for simple cases. But what happens if we had an input or a force that doesn't look like anything in particular? So u of t is just equal to this function here, changing over time. So how can we actually solve our linear system for a more complex case like this? So let's start by looking at a special case. And that special case is an impulse. So let's go over the case of impulses. So an impulse is an input that is infinitely large, but is applied for a very small and infinitesimal amount of time. So if we were to draw out our input u of t, represented by our blue line here, from times t just a little bit before 0 to just a little bit after 0, our input would look something like this, a big jump up that comes straight down again. Now that's what our impulse is. What does that do to our state x for our first order system that we were going through here? Well, our state was at a constant value, and suddenly it's going to jump up and then kind of go into a free response, a exponential decay if it is stable, which we'll get into later. So if we zoom in on these two graphs, we can see that what our impulse will look like is pretty much like a rectangle. From 0 minus to 0 plus, if we zoom in a lot. And what happens to x is that it essentially jumps between those two times. So our change in time is essentially 0 between 0 minus and 0 plus. It's essentially 0 there. That's what an impulse is. An impulse can essentially change your initial conditions. An important function relating to input functions or impulses in general is the Dirac delta function, which is represented by delta t, which is the unit impulse. And the definition for this guy is delta t multiplied by dt integrated from 0 minus to 0 plus, a very small period of time, is going to be equal to 1. So now that we know what our impulse function is, let's get our impulse response. So impulses, they don't really exist physically, but some cases look like them. So for example, if two objects collide together and they bounce off of each other or they change each other's velocities, that kind of looks like an impulse physically in the world. Now, an impulse response, that is the solution to the equation of motions when an impulse is applied. So let's go back to our state space model for x dot is equal to ax plus bu, and we have some sort of initial condition at 0 minus, so before the impulse, and we're applying a unit impulse to the system, applied from negative 0 or 0 minus to 0 plus. Now let's say the difference between 0 minus and 0 plus is this epsilon here, and I've drawn a little figure to try and explain that. Our impulse, essentially, what our input would be in this case is this time here between 0 minus and 0 plus, that is epsilon. The height of this impulse, therefore, to be equal to the integral of 1 for our definition of our impulse function, that's going to be 1 over epsilon here. So what happens between 0 minus and 0 plus? Well, we're going to have our x dot, which is approximately going to be equal to x0 plus minus x0 minus over our epsilon. And then we're going to just plug in 0 minus in the value for u here for our state and our input respectively. And this is essentially just approximating this using like a forward Euler or the definition of a derivative, actually. We're going to take this epsilon, we're going to shift it over here, multiply everything on both sides by epsilon. So now we get x0 plus minus x0 minus is equal to epsilon times the same thing that we had before. But these two epsilon here, they're going to cancel out. So we're going to be just left with b. We're going to move our x0 minus over. And then now this last term here that's still multiplied by epsilon, that's going to go to 0. So essentially what this does is our initial condition from before was this x at 0 minus, just before the impulse. And now our new initial condition just after that impulse is x0 minus plus b. So now we have our shift in initial conditions. That's what our impulse response pretty much explains. So now let's go through a more complicated case, the convolution integral. So we have that generic input we had earlier. Let's actually just break it up into separate little pieces here. This is like a series of impulses, and each one of these pieces is essentially infinitely small. Now, if we use something called the convolution integral, we can get the general solution for LTI force problems. So what do? We figure out what our impulse response would be. We can pretend the input is our our Dirac delta function, and our initial conditions are 0. We're going to solve our convolution integral, which is going to be this complicated expression here, but it's actually not too bad, where we have x of t is equal to the integral from negative infinity to positive infinity of h of t minus tau times f of tau times d tau. Or in other words, you can reverse those and you could have f of t minus tau and h of tau instead. Now, h is our impulse response. F is the actual input that we have for our system. So u, for example, in this case. So for LTI state space model with initial conditions, what does the convolution integral give us for our total solution? Well, our final solution, if we have this linearized system for our state space model, our linear state space model, our solution for our states with respect to time will be e to the a times t, where a is our matrix that we had before, it's a state matrix, times our initial condition vector, plus essentially what is amounting to our force response, the convolution integral, the integral from 0 to t of e to the a, now t minus tau, times b times u of tau d tau. This is our force response, or the convolution integral. The other part is our free response for our system. And this is assuming that we're starting at t is equal to 0. You need to make adjustments if you didn't start at t is equal to 0. Now, what is e to a matrix? That's a little bit of a weird expression. Well, it's called the matrix exponential, and it has a specific definition to it. E to the at is that matrix times time to the power of I over I factorial, and you do that from I is equal to 0 to infinity. And there's approximations out there that can provide that. So this is the general LTI solution for any linear time invariant state space model. And that's it.